Can you see my desktop?
Yes.
Yes.
So you should see the cross section of Mount Amiata, the one we have seen yesterday, with the geothermal field that is contained in the lower part of the section here, within the anhydrite formation. So let's see how you approach the problem. If you would like, for instance, to devise an experiment, an analog experiment, which means an experiment that will resemble what's going on in the field, but actually in a small lab experiment. To do this, you need your experiment to have similarity with reality. And because of that, you need to define what are the most relevant dimensionless parameter that describe the field geothermal system so that you can have similarity at much reduced dimensional scale in the lab. These also allow you to understand what are important parameters that you need to consider. Even if you are a geologist and you go in the field, it's always very important to have an idea of what these dimensionless parameters are so that you can create an image, a correct image of your geothermal system in your mind. Are you aware of the Buckingham Pi theorem? Please say yes or no. I cannot hear any of you. I would argue that most of you don't know what the Buckingham Pi theorem states, but is a very, very important theorem and at the same time very simple. The Buckingham Pi theorem states that given a natural system, the number of relevant variables minus the number of dimensions that are used in these variables give the number of dimensionless parameters that describe this system. So I guess, can you see also my Word document here?
Yes.
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 So the number of parameters minus the number of dimensions is equal to the number of dimensionless parameters that you need to define to describe your system. So let's try to let's try to define these parameters and how you go around defining these parameters. Now, the first are that you need to define what parameters, what variables are important. The first group are the geometric variables. So if you have a cross section like that, and you have your geothermal system down here, what are these geometric parameters? Now, go back to the lessons, yesterday's lessons, we said that the first is the heat source. So we know that the heat source is at depth here. How deep? Well, 5 to 7 kilometers. So say 5 kilometers. So the depth is H, we will call it H, is the first very relevant parameter that is going to be in our geometric list. So let's write here geometry. H, and H, the depth will be in meters. That's how you measure your length scale. The first rule is this. Then we go to the third rule that we had yesterday, and if you remember, was the recharge. I need to know and to look for the recharge. So if you go my cross section, I see my geothermal field is out here, where the wells are, and I need to know where the recharge is, and the recharge area we said is Mount Amiata, and therefore the distance that you have to the recharge area will be a good horizontal dimension for your system. So we will write our system, our length scale, horizontal length scale, still in meter, as L. So geometry, well, we are done. I guess in geometry, the two main parameters is how deep your geothermal system is, how wide your geothermal system is. Now, by the way, this horizontal dimension that you see here between your geothermal field, actually the farthest edge of the geothermal field and the recharge area, is in the order, this as well, about 5 kilometers. This is equal 5 kilometers. That's right, 5,000 meters. And instead H, we said, is something between 5,000 and 7,000 meters. Now, other parameters that you feel are important, well, let's see if we are going to have convection in this geothermal system or advection in this geothermal system. This means that you are going to have fluid motion. So you need some to define some dynamic parameters. I would appreciate if you can interact with me in this and not being silent. So what kind of dynamic parameters you feel will be involved in describing your geothermal system?
The temperature.
Well, temperature is not so dynamic. It's more like your heat source. So let's put another down here, energy, and put the temperature T, which is going to be measured in centigrade. Now, when you define these variables, you really like to have as parameters the maximum values for your parameters. So the temperature, say, would be the maximum possible 350 centigrade. But let's go to something more dynamic. What are the forces that act in the system? Now, when you do this, what you like to have is actually trying to follow the conservation equation. So conservation of mass, conservation of momentum. So the equation, all the sum of forces equals 0, and then the conservation of energy. So if you are talking about what is forcing or resisting the flow of your system, what parameter you think they should go in? Something very simple. What is the major force that acts on Earth?
Pressure.
Pressure. You said pressure. Yes, correct. Pressure is a good, and because your fluid is going to be driven by sort of a pressure difference. Whenever there is a pressure difference, then your fluid is going to move from high pressure to low pressure. So always in the negative of the gradient of the pressure. So we call it P pressure, and it's going to be measured in Pascal. But Pascals, what are Pascals? Sorry. Pascals are, a pressure is a force of an area, and a force is a mass times an acceleration. So you're going to have kilograms, mass times an acceleration. So meter divided second square divided by an area, so will be meter squares. And this meter will cancel with this. Let's write this way. So pressure is good. Give me something else. This is really awful. What is the most important force on Earth? Natural force. Gravity, right? So I will add the acceleration of gravity, g, and the gravity is an acceleration, so it will be meters times second squared. Now, from the dynamic point of view, both pressure and gravity, particularly gravity, they will need to act onto something, right? Onto a mass. To get a force, you don't just need the acceleration of gravity, but you also need to have a mass. And therefore, you will have the density. Density, I would like to write rho. Density, wait a minute, let's write density of the fluid. we take a little bit this. Density of the fluid, what are the units of measurement of density? What are the units of measurement of density? Kilograms, oh, sorry, apologize this. Kilograms divided meter cube. Density of the fluid, because it's the fluid that is going to be moving around, all right? What else? You think this is sufficient or not?
I think sufficient.
Okay, let's try to see if it is sufficient. Okay, so we have how many variables? 1, 2, 3, 4, 5, 6, correct? 6 variables.
Yes.
And how many dimensions? Meters, kilograms, second, temperature, centigrade, so 4.
Yes.
So, but by doing this, you think you will need only 2 dimensionless parameters. What could they be? Okay, very simple. First, we do a geometric parameter, a geometric ratio. So H over L, pi 1. Very easy. First, you write H over L is always there. The main ratio between main dimensions of the system. So let's try to write the pi 2. What will you suggest? Well, for instance, let's try to use a dynamic and try to put pressure on top of the fraction that defines the dimensionless parameter. If I put pressure on top, then I have kilograms divided second square times meter. So if I want to put pressure on top, I need to have some other parameter that has density, that has a kilogram in, and this is density. So I need to put density at the bottom. Okay. Now, density is, let's try to do it here. This is pressure. copy. Okay, these are the dimensions of pressure. Let's divide also by the dimensions that are contained, copy. All of this is divided by these other dimensions. So I can start canceling kilograms. I can cancel kilograms, and I can cancel this meter, leaving meter square here. And so this meter square divided by second square. This is what I'm having now. So to be able to cancel this, I need to divide this, for instance, by G, by the gravity. And if I divide by gravity, I will be dividing by so seconds will cancel out, meter cancel out with a square here. And so I need to divide also, say, by H, for instance. I put a meter here, and so this meter cancel with this. So we finally get a parameter that is dimensionless. And we have a pressure against the density of the fluid, the acceleration of gravity, and the vertical dimensions of our system. By the way, rho FGH is the pressure that I have on top of our magmatic intrusion, the depth, the pressure at the depth of our magmatic system. So the pressure that I have at the bottom of our convective cell. So this is a good parameter. So are we all done? Or is there anything else that is missing? Well, we are not using temperature. So we need at least, there is nothing we can scale temperature to. So the number of our parameters is insufficient.
Yes.
So we need to add more parameters. In addition to this, pressure against our hydrostatic pressure is the forcing that allow the fluid to move. But what is happening, for instance, who is equilibrating this force? The force that pushes the flow across our rocks is equilibrated by what? Is there any idea from your side?
No, Professor.
Sorry?
No.
Well, it's very simple. There are two other parameters which are extremely important in determining the resistance to flow. For instance, how this fluid could be gas and have a very low viscosity, or could be very dense water and being very viscous. So if I have my pressure, this pressure is going to be equilibrated in part, at least, by the viscosity of the fluid. How easily the fluid can flow. One of the parameters that determines how easily the fluid can flow is the viscosity of the fluid itself. So the viscosity is going to be mu, and are going to have dimensions of Pascal second. That is kilograms divided, kilograms divided by Pascal was second squared by meters multiplied by second, so it's going to be seconds meter.
Yes.
So these are our dimensions for the viscosity. Let me put the viscosities. Okay. Okay, then what is another, because not only the viscosity is important, but for instance, how big the pores of the rock are. The pores of the rock are like pipes. If I have very thin pipes, even if I have the same viscosity for the fluid, it would be hard to push the fluid through, compared if I have very large pipes. So what is the parameter that is related to the medium that determines how easy the fluid flows through your system, your rock? And this is permeability. So the permeability of the rock is the other very important parameter. Permeability is expressed as K, and the dimensions of permeability are meter squared. So in defining my dynamic parameters, I have forcing forces, the pressure, the gravity, but then I have some characteristic of the fluid that I need to deal with, and it's the density and the viscosity of the fluid, which are important. But also some parameter that describes the rock matrix in which the fluid is flowing. So would you agree with this kind of set of these at least two additional parameters that I've added in?
Yes.
And so, but by doing this, we have added 2 additional parameters. So it'd be 1, 2, 3, 4, 5, 6, 7, 8. From 6 we go to 8, but still the units are 4. 8, so I would go to 4. 4 parameters, and we'll try to define them, but still I have nothing to go against the temperature so that I can cancel down the temperature. Now, what I could do here is say, look, I'm not really very interested in the temperature, but I am interested in the temperature, the maximum temperature, and the minimum temperature of our system. If my system is all at one temperature, in the end, I will not have convection. So what are a parameter that from the dynamic point of view could be important? For instance, I know that my temperature, if my fluid is at high temperature, is less dense than if my fluid is at low temperature. Okay, then I will need a coefficient of thermal expansion. Coefficient of thermal expansion, for instance, I call it alpha, and has dimensions of 1 over temperature. Coefficient of thermal expansion is about, for the water, is about 10 to the minus 3. 1 over centigrade. So now I go to 9 parameters. Minus 4, and I have 5 dimensionless number. However, if this could be perhaps sufficient to describe now. So I have set up only 2 dimensionless parameters. I need at least 3 more for describing my system. So what will be these dimensionless parameters? Pi 3 equals, pi 4 equals, and pi 5. Well, let's talk about pi 5. Very easy to do. If I go copy alpha times temperature. Now this is dimensionless, all right? So this is very simple. Then I would need to add 2 more parameters for So, first of all, I could write something like this. Let's use K, for instance. Let's start from K, from mu. So how am I going to scale the viscosity of the fluid? So the viscosity of the fluid is actually interesting to scale it against, for instance, the pressure. If I scale it against the pressure, it's pretty interesting. What we have here is a second square. The pressure scales as kilograms divided second square per meters. Now, my viscosity has just 1 second at the bottom, so I need my my viscosity to be squared to be able to cancel with this second square of the pressure or of the gravity. My viscosity needs to have a square. And therefore, I need here to sorry about the so if I put viscosity square, then I need to have viscosity square will be kilograms squared divided second squared meters squared. So to cancel the kilograms squared, I need to have a density squared, for instance. Viscosity, so the density and the viscosity, they both have, so they need to be on different sides of the equation. If I go here, copy density of the fluid. And this must be squared as well, because I need to have it cancel with the square. So I have here kilograms squares, they cancel with this kilogram squared, and then I have divided the density by meter cube, so it's meter to the 6th. So that here the density, the kilograms cancel, and meter square will be meters to the 4th. Meter to the 4th. Then I have second square, so I have second square here. Second square. Okay, so I'm left with this. And I have density and I have viscosity. So what I need to do, for instance, is to cancel second square, I can use gravity. for instance. Meter square. So if I multiply the density square by the gravity G, I'm able to meters divided second squares, and these second squares cancel with this, and this meter can cancel with this cube. And to do this, to cancel this, I just need to add at the top h cubed, h to the third. Okay, and then the last, I will need to use my permeability. So this parameter pi3 is sort of, as you see, there is a rho gh here, and that is the pressure, and I have a viscosity. So sort of a relation between the forcing pressure and the resisting of the fluid due to viscosity. Now, I would like to have perhaps the permeability against the pressure. So this I will have meter square for K, and then I would like to add and to scale this against the pressure, if possible. So meter square, meter square, meter square, meter cube, or I could simply try meter cube. So let's try to put here, say again, the pressure. Pressure, and pressure will be, we said, kilograms divided meter square, sorry, second square, and meters. So PPP, meter is at the bottom, here is at the top, and so I need to here to divide by P, so I need to divide this, and I need to add a P square. So I have kilogram square second, sorry, to the fourth meter square. And so I can cancel this meter square with this here, fourth. Now I can use, I will need to use my gravity. My gravity is I need to use a gravity square. I need to put my gravity square and my P square. So with my gravity, I will have gravity or meter gravity squared divided second to the fourth. So the second and the second cancel away. And then I need to cancel my kilogram squares, and that I can do that by adding the density. Copy. The density itself is going to be squared. Sorry, I made a mistake here. Okay, so my density is going to be kilograms squared divided meter cube, meter to the sixth. So here I can cancel this and put 4 here, and this will go away, and this will go away. So I need to add here AH to the fourth, H to the fourth. So, and I've created my dimensionless number, my dimensionless number. Now, probably there are even more parameters that are important, but this, if I consider that these are my variables, then I would argue that these are correct dimensionless parameters to scale my experiments, so that my experiment actually resemble what's going on in the field. What could be other parameters important? Thermal conduction, for instance. If I consider that conduction is important, then I will need to add conduction. If I consider that other parameters are important, for instance, I would like, for instance, to add maximum temperature and minimum temperature to see the temperature difference. Then I would like to add not only just one density, but the density at the maximum temperature and the density at the minimum temperature. And accordingly, I will need to vary my dimensionless parameters. Now, how do I know that these parameters are sufficient? The Buckingham Pi theorem tells me that these are sufficient. How do I know that these are the best possible dimensionless parameter that I can find? That you cannot know just by looking at the geometry of our system or your system without going in a detailed analysis of your equations that describe the system. Through your equations, you're actually defining the correct dimensionless parameter or the best way to represent them. But even with the Buckingham Pi theorem, you have sufficient data to describe dimensionless parameters and to make an experiment that is dynamically similar to what is in the nature. Do you understand the process that we have been through, that we went through? Or very little? I cannot hear you because all your microphones are off. Pier Giovanni, sono stato abbastanza... have I been clear enough? Ettore, what do you think?
Yes, quite clear. It's,
Okay. So did you know the Buckingham Pi theorem before?
no, maybe with another name.
Okay. Okay. So, but is the principle of scaling. If you have scaling, the principle of scaling to be able to design a correct experiment in the lab that will resemble what's going on in the field, as a first approach, use the Buckingham Pi theorem. And this is a simple way to use it. Now, in the next step, we will go through the equations that describe the geothermal system, and we will see how these dimensionless parameters that we have defined in the Buckingham Pi theorem may result directly from the equations. Now, the equations are better in the end because they not only give you dimensionless parameters, but also give you the best way to write them. Mi si è bloccato tutto. Okay. Please tell me when you see the new document that I have opened.
Yes, I see it.
No.
So there are fundamentally three equations that describe the flow in porous media. And of course, they are based on the equations of conservation. The first of them is the conservation of mass. Then the conservation of momentum. Now the momentum equation, as is momentum is a vector, is not a scalar, and therefore you have an equation of momentum that must be conserved in the different directions of space. So actually you will have three equations of conservation of momentum, say in the x direction, in the y direction, and in the z direction. And then you have conservation of energy. Energy again is a scalar, so you have one equation that describes the conservation of energy. I apologize, it's going to be a very long process, very boring, but I think it's very useful and very important. And I would suggest you to take pen and a piece of paper, and you actually write again all these equations that I'm going to show you, and you go again through this process to try to understand really carefully what's going on in the scaling of the equations. So the equation of conservation of mass, can you actually see well? Yes, you should see it, yes.
Yes.
Conservation of mass. I'm writing it only in 2 dimensions because the third dimension is just equal to the x direction and the y direction, the two horizontal directions, are approximately equal in the scaling, and the reason is that both are horizontal. So on both x and y, the gravity acceleration doesn't appear. Gravity acceleration appears only in the z component. And just to make it more simple and easier to follow, so I'm going to do the scaling of the equations only in 2 dimensions. Rho F is the density of the fluid, of course, is the fluid is the only that is moving through the system. So the density is going to be the density of the fluid. The density, of course, resembles the mass. So the density of how the density given a unit volume, how the density varies in this unit volume through time is the third term. If there is density of accumulation into this volume, then the density increases. If the mass decreases in the volume through time, then the density decreases. How, for instance? Well, easy. Suppose that you have a fluid that is hot, and this fluid is just losing temperature. That means that the density of the fluid by losing temperature is increasing. The energy goes away, so the density of the fluid increases. However, the volume of the fluid, if the volume of the fluid doesn't change, then actually the density within that volume decreases. If the volume shrinks, then the density can remain constant. But how the density changes in your unit volume in time is described by the first term. The second and the third term are the advection terms and describe how the mass per unit volume, the density, is brought into the volume or exit through that volume in the x direction and in the z direction. You can have mass coming in the x direction and not going out in the z direction, in the x direction. That means that it's going to be going out in the z direction by conservation of mass. Or if mass is coming in the x direction and no mass is going out, that means there is a density increase in time. So the first term is going to be important. So the accumulation of mass in the unit volume in time must be equal to the mass that comes in minus the mass that goes out in your system, both in the x direction and in the z direction. Is it clear?
Yes.
Now,
Yes.
to be able to understand well and to be able to define your dimensionless parameters, you need to modify this equation so that the variables, particularly the density and the two velocities, velocity in the x direction, velocity in the z direction, how much this velocity change in time. So you need to scale your variables so that these variables change between 0 and 1. So you need to do two things. First of all, you need to turn each parameters dimensionless. Then you need to make this parameter vary between 0 and 1. So if each of these parameters vary between 0 and 1, then you can compare them one to the other. Let's see how this process in which you need to reach two goals. First, make each parameter dimensionless. Second, make them vary between 0 and 1. So let's see how this is achieved. I need to define a set of variables which are dimensionless. And so, say the density of the fluid. And I call the dimensionless density rho asterisk, rho of the fluid with an asterisk on top that indicate your dimensionless parameter. So I scale my density of the fluid with the maximum density of the fluid, which I call density of the fluid at 0. 0 means the lower temperature. In geothermal energy, the lower temperature is usually the surface where I have the origin of my reference system, and this is why I call it rho F0. So this is my maximum density in my system. So by scaling the density of the fluid to my maximum density, I achieve a parameter that is dimensionless. And in addition, this parameter varies between 0 and 1, because when the density is 0, say for a very low pressure gas or vapor, then my scale density is 0 because rho F is 0. When the density of the fluid reaches the maximum density, which is the rho F0, then the value is 1. And so my scale parameter not only is dimensionless, but also can vary only between 0 and 1. Do you agree with it? Please say yes or no, if you can.
Yes.
So then I can say that my density of the fluid is equal to the maximum density times my dimensionless density. You simply bring the denominator to this other side of the equal sign. The same I can do for the velocity in the x direction, which I scale to my supposed maximum velocity of the fluid. Maximum velocity of the fluid, which probably I don't know. However, I can imagine there will exist in my system a maximum velocity. So I can scale that and find out that my dimensioned variable velocity in the x direction can be scaled, can be substituted by my scaling velocity, maximum velocity in the x direction times my scaled parameter. Velocity is a vector, so I have also the velocity in the z direction. And again, my scaled velocity in the z direction is equal to my dimension velocity in the z direction divided by the maximum velocity in the z direction. And here is a mistake. Let's see if I can correct it on the spot. Oh no. Oh yes, yes. Okay, sorry about this. Again, both velocities in this case can vary between 0, both scaled velocity vary between 0 and 1. Wherever the velocity is 0, very far away from my system, then the scaled velocity is 0. Then the velocity can increase only to the maximum velocity, and therefore their fraction, the scaled velocity, is 1. Do you agree with this? Please say yes or no. Or any questions?
Yes.
What is important about these velocities? These velocities are not the actual velocity of the fluid within the pores, but are the Darcy velocities. And that is the velocity through the cross-sectional area of the rock. So the pores, the actual pore space or pore area is much smaller than the cross-sectional area of the rock. So the actual velocities, the true velocities of the fluid, are much higher than what the Darcy velocities are. Then we need to scale the coordinates x, z, and t. And so again, I do the same with the time. Time is scaled to the maximum or characteristic time of my system. I don't know what that is, or perhaps I do know what that is. However, it does not really important as long as I can imagine that there is a characteristic time for my system. And I can scale my time, my dimensional time, to the maximum or the characteristic time of my geothermal system to obtain T asterisk, the dimensionless time. And again, I can say that the dimension time is equal to my dimensionless time times T asterisk. Same argument I do with X, and same argument I can do with Z. Then I can substitute in my equation the dimension variables with my dimensionless variables. And this is the equation that I get. If I look at the first parameter, I can see that the derivative of my maximum density times my dimensionless density, since the maximum density is a constant, I can take it out of the derivative. And so the derivative of the differential of my dimensionless time times my characteristic time of the system, this characteristic time is a constant, I can take it out of the differential. Does it make sense to you? Please say yes or no.
Yes.
Okay, so the same I can do for the transfer of mass, or the differential of transfer of mass in my unit volume. I have a velocity, maximum velocity in the x direction, and that is a constant. I have a maximum density, and that is a constant, and I can take out of my differential. And so I can take my maximum dimension of my system L out of the differential. And the same I can do in the z direction. So I end up having 3 dimensionless differentials, and all the dimensions taken outside of the differentials. Now, because I have a 0 on the other side of the equal of this equation, conservation of mass, then I may divide the full equation by one of these parameters. For instance, by rho f0v divided by h. And I can come up with a second, or well, in this case, equation number 3 that you can see here. What is interesting is that I can cancel out of the equation the maximum density of my water. And I end up with 2 dimensionless parameters. Two dimensionless parameters, h divided v times a time, so it's meter over meters, and is seconds over seconds, practically this second dimensionless parameter. What is important here? Again, applying the Buckingham-Pi theorem, we had 1, 2, 3 parameters, and each of these had some dimensions. So 3 minus 1 equal to 2, and so I get here 2 dimensionless parameters. What is the different approach relative to what we have done before? Before, we had no idea about the equations. We were just guessing, and that is very important because many times you're not able to actually not even write an equation for a natural system. Natural systems are so complex that in many cases you cannot even write an equation. But even if you cannot write an equation, the Buckingham-Pi theorem allows you to write dimensionless numbers, which are essential to scale down your experiment in the lab. On the other hand, by using the equations, you are able to define what are the best way to write your dimensionless parameters, as we see here. Why this is the best way to write these parameters? Now, the differentials, all the differentials here, contain variables which vary between 0 and 1. So we are saying that these variables are of order 1. Hopefully, this is a hopefully, but the experience tells that is actually correct, this whole, hopefully, not only the variables in each differential vary between 0 and 1, but also the differential itself vary between 0 and 1. So these three differentials are of order 1. This is the experience that tells that even though we know for sure that only the variables vary between 0 and 1, since the differentials are made by fractions between variables that are dimensionless and vary between 0 and 1, the differential itself vary between 0 and 1. They are of order 1. Please say yes or no if you understand this reason. This is very important. I cannot hear any of you. Do I have to repeat, or is clear enough to you?
Yeah, I think if you can repeat, because...
Okay, I will repeat. I'm very happy to do it. So we have seen that each variable in the three differentials that we have vary between 0 and 1. The density of the fluid varies between 0, a very low pressure gas or vapor, and the density of water at low temperature, so your maximum density. The scaled, since they are scaled to the maximum density, they can vary between 0 and the density vary between 0 and 1. We have seen that in this equation out here. So each of these variables vary or can vary between 0 and 1. So if the density varies between 0 and 1, the scale density and the scale time varies between 0 and 1, the fraction between these two differentials varies between 0 and 1. In principle, this is not, could, theoretically, mathematically, perhaps could not be true. But in practice, in reality, the experience tells that it's true. So this differential itself varies between 0 and 1, which means we say it is of order 1. This is the maximum value that this differential can take. The same, these other two. Rho asterisk varies between 0 and 1. The velocity in the x direction varies between 0 and 1. The dimension of x varies between 0 and 1. And so the fraction that we have here varies between 0 and 1. It's not only dimensionless, but also varies between 0 and 1. And we say, and we state, is of order 1. And the same is true in the z direction. The density of the fluid, we said, varies between 0 and 1. The velocity, the scaled velocity varies between 0 and 1. The z component varies between the surface and the depth, again, varies between 0 and 1. And all the dimensions and the maximum values that the parameters can achieve are contained in these two parameters, in the parameters that form this two-dimensionless number. Now, in front of this differential, we have a 1, we have nothing here. So this is of order 1. This is of order 1, and this is of order 1. Now, suppose that this first parameter, this first dimensionless number, is not of order 1. It's a very large value. Suppose that it's 1,000 instead of 1. Then I'm multiplying 1,000 by something of order 1, which means this first parameter, this first term here, is of order 1,000. Now, compared to this, which is of order 1, is much larger. So the first term, in this case, will be much larger than the last term. What does it mean? That this first term is much more important than this last term. And you can throw this term away. Same applies here to this parameter here. Suppose that this parameter is very large. Say is 1,000. So I have here a term that is of order 1,000 against a term here that is very small, is of order 1, is much smaller. So I can throw this away. Let's do the opposite. Suppose that h over vt, it's a very small term. And this fraction, this differential, is of order 1, which means that multiplying a small term by something of order 1 is a very small term, say 10 to the minus third. So this first term for the second case is much smaller than the differential, the advection of mass in the z direction. So I can throw away the term that tells mass accumulation in the unit volume. And the same is true for the second term. Now, why I have divided the equation number 2 by rho F0V divided by H and not by the other? Well, you want to divide by the term of these 3 that you have here that is the largest. So you need to find sort of rule of thumb values to this, find out which term is the largest, the accumulation term, the mass transfer in the x direction, mass transfer in the z direction, which is the largest, and then you divide by it, so that the term that was the largest has a 1 here, and the other 2 are either equal or very small. So you can either throw this away, these 2 fractions away, or you cannot throw them away because these 2 parameters here, these 2 dimensionless number here that we have, themselves are of order 1. Please say yes or no. I would really appreciate if you say yes or no, because I can repeat as many times as you want. But if I go ahead, it's important to understand what I have done here. It's a simple mathematical trick, but it's very relevant for understanding which terms are important.
So the only doubt I would say it's how do you decide which is between this term the bigger?
You decide this by giving some values. For instance, density. Well, density of the water is 1,000 kilograms per cubic meter. That's just about the maximum value you're going to get. So H, what is H? Well, H could be, the depth of your intrusion, 5 kilometers, 5,000 meters. What is your velocity? Well, it's not going to, for sure, going to be meters per second. Your maximum Darcy velocity, it can be 10 to the minus 3, 10 to the minus 4. So you are actually giving the values, and then you compare them, and then you see which is the largest. Now, the experience in geothermal energy tells you that the most important term of all is the vertical flow, because you need to bring heat from depth to the surface. So you want to have that number. Remember, the first thing important in a geothermal system is where is your heat, how deep it is, because you want to bring to the surface that heat. So you always want to have this third term. You cannot avoid that. Otherwise, you will bring, like is done in surface aquifer, your water flows horizontal from low temperature to low temperature. And you don't have a geothermal system. To have a geothermal system, you need, where is my heat? Down at depth. So I need to bring the heat up to the surface. And therefore, I need to have this third term. Second term. The second term here, we said the second most important thing you have to think of, the second was impermeable layer. The third one is recharge. Where my recharge is. So I need to go somewhere to find out where the geothermal system is being recharged. So the second most important term is this here, is the velocity is the velocity of the mass transfer in the x direction. You need to transfer mass from somewhere far away to somewhere else where your geothermal system is. Then, third in relevance is mass accumulation, and through time, and mass decrease through time. So suppose you are at the beginning and an intrusion is placed at depth. Where your geothermal system is going to be at the beginning is going to have cold water, because your intrusion, your heat source has just come in. So this first term is related to how much time the density of the fluid will decrease because it's increasing temperature. And that is a long time. So in order, you have the third term is the most important one. The second most important one is the velocity in the x direction, because it allows you for the recharge to exist. And the third most important is the density variation in time, because it takes a very long time to variate that density. It takes a very long time to create a geothermal system. The rule of thumb is 100,000 years. or better say between 10,000 years and 100,000 years. That is the time that you need to create a geothermal system. Now, we said yesterday the rule of thumb to exploit a geothermal system is to cool down a cubic kilometer of rock by 10 degrees, but in 10 years, 10, 30 years. So you are decreasing the temperature of your geothermal system only in 10, 30 years against the 10,000, 100,000 years. So once you have exploited your geothermal system, is exploited. You're never going to recharge again. You're never going to wait 100,000 years for the system to become again hot. And this is why when it's used in this way, particularly to produce electricity, geothermal energy is not renewable. It's an alternative energy for sure, but it's not renewable because that heat it would take too much time to recover. Geothermal energy is very similar to a quarry. You have a mountain, in the mountain you have a quarry, you take out the rock. Well, when you have taken out the rock, that quarry is not renewable. A renewable quarry is, for instance, the sediments in a river, because you take out the sediments and then next year with the floods, the river will bring in sediments again. So, in quote, a quarry in a mountain is not renewable. A quarry in the riverbed is renewable, or at least in part is renewable. And so this is geothermal energy. And this is why I like to divide this three terms equation of mass conservation by the third term, because I always want to have the third term. I know that is important. And so I'm going to divide by the dimensionless parameter that I have in front, by the parameter that I have in front, so that I can get the two dimensionless parameters. Any question?
No.
Sorry.
No.
Okay. So we have achieved to have these two dimensionless number, pi 1 and pi 2. What is the next step? We said that the second parameter is the second most relevant, and the third parameter is the third most relevant pi number. So if I want just a hot plume of water coming to the surface, for some reason you don't have the recharge, but in principle suppose that you have a hot plume coming to the surface, then velocity in the x direction are nil, and the density changes are nil, and only the third term is important. But if you want to have recharge, like you have in most geothermal systems, if you want to have recharge, then the dimensionless number HU divided VL must be of order 1. Otherwise, it's too small and the whole second term goes away. So you will have to write these two. The first term, H divided by VT of order 1, And equation number 5, HU divided VL of order 1. If you want to have, go back to the same equation, if you want to have important recharge, okay, you need to add in, you need that this pi number, HU divided VL, be of order 1. And the same, if you want to have important the heat source at depth, then you need to have H divided V tau be of order 1. So in the end, if you want to have important the 3 terms in the mass conservation equation, then you need H divided VT be of order 1 and HU divided VL be of order 1. Therefore, you can determine what is your time scale for your system, your characteristic time. Vertical velocity divided by the distance in which it has to travel. And even more interesting, you know that your horizontal velocity is equal to the vertical velocity multiplied L over H. So your horizontal length divided by your vertical length. So why we did this exercise? While by applying directly the Buckingham-Pi theorem, we were not really able to tell which were the best pi number you could write. By using the equation mass conservation, we are able to tell which are the characteristic time of your system and the characteristic horizontal velocity of your system. So you are able to cut away some of the variables that were present in the list before for a pi number that, let me pull out the, okay. We had our pi number, and for instance, we had pi 1, H over L. Well, something H over L over H, we have it here, but we know that H over L is not so important as much as it is important H over L, U over V. That is the pi number that is important, and this is because of mass conservation. So by using mass conservation, we were able not only to write the correct pi number, but also the best pi numbers. Please say that if you understand this argument, say yes or no.
Yes.
Yes, it's clear.
Good. So in the second part of today's lessons, we are going to go to the scaling of energy, of momentum equations and the energy equation, and find out all the other relevant pi numbers that interest geothermal energy.